So let's talk about quantization.
All right. Quantization is basically the process of moving from a smooth, continuous system to a discrete one. In physics, we often use it to explain how quantities like energy, momentum, or angular momentum can only take on certain distinct values. Think of it like turning a ramp into a staircase. In quantum mechanics, this leads to things like quantized energy levels in atoms, where electrons can only occupy certain allowed states.
How does the wave function and the quantization is related, and that wave function help us to capture the quantization information?
The wave function is like the mathematical heartbeat of a quantum system. It describes all possible states the system can be in. When you solve the Schrödinger equation, you get wave functions. Now, those wave functions must satisfy certain conditions, like boundary conditions. Those conditions restrict the wave function to certain shapes or patterns. Each allowed wave pattern corresponds to a quantized energy level. So the wave function not only encodes the probability of finding a particle somewhere, but also shows us that only certain discrete energies are possible. That's the quantization.
But the wave is itself is quantized. That is what you are suggesting.
The wave itself isn't quantized in the sense that it's chopped up. Instead, the wave can take on many shapes, but only certain shapes fit the physical scenario. Those allowed shapes correspond to discrete, stable energy levels. So the wave function is smooth, but it's like a standing wave on a guitar string. Only certain notes can resonate. Quantization comes from which wave patterns are allowed by the system.
Okay, can you give one real example that it captures?
Sure, take the hydrogen atom. When you solve the Schrödinger equation for an electron around a proton, you get wave functions, orbitals, that only exist for certain energy levels. You'll see discrete energy states like the well-known n equals 1, 2, 3 levels. The wave function's shape changes with each level, and each shape corresponds to a quantized energy. That's why hydrogen spectral lines are distinct, capturing that quantization directly in measurable form.
So in light matter interaction also we talked about this major principle quantization, and this quantization principle is plays a role in every aspect because everything which we study itself is quantized.
Exactly. In light matter interaction, quantization shows up everywhere. Light is quantized into photons. Each photon carries a discrete amount of energy. Atoms or molecules have quantized energy levels. When light interacts with matter, it can only be absorbed or emitted if the photon's energy matches the difference between these quantized levels. So, whether it's absorption, emission, or scattering, quantization dictates the allowed processes and outcomes.
So what are the first of all theoretical and experimental evidence of this theory, and how did it helps in a very better way?
Theoretically, quantization comes straight out of solving quantum mechanics. Schrödinger's equation, for instance, predicts discrete energy levels. Dirac and others built rigorous mathematical frameworks that showed why only certain states are possible. Experimentally, classic evidence includes things like the hydrogen spectral lines. When you shine light, you see specific colors matching those energy jumps. The photoelectric effect, where light ejects electrons only if above a certain energy, is another key experiment. This has helped us build everything from lasers to semiconductors. In short, quantization let us predict and control matter-light interactions, powering modern tech.
If we not see the quantization principle in the Schrodinger equation, then that Schrodinger equation will give any solution that.
Oh, it would still give solutions, but without the boundary conditions that lead to quantization, you'd get continuous ranges of energy. In other words, you'd have infinite possible energy values, no discrete steps. The Schrödinger equation itself is just a tool. Quantization comes from applying conditions, like trapping a particle in a finite region, like an electron in an atom. Without those conditions, you'd get a continuum of solutions. Interesting, but not like the real atomic world.
So this is very intriguing that trapping a particle in a finite region, like a electron in an atom, or in that atom is hydrogen atom, and that has a Coulomb potential. That is what we actually frame a particle in a potential well with the boundary condition.
Exactly, you've got it. The Coulomb potential in a hydrogen atom acts like a well, an attractive region where the electron is bound. The boundary condition is essentially that the wave function must vanish at infinity, meaning the electron can't just escape to endless space. Because of this trapping, only certain wave patterns fit, like standing waves on a string. Those allowed patterns give you the quantized energy levels, and that's why electrons in atoms have distinct, stable states.
So, when electron evolves inside the hydrogen atom with the Coulomb potential, uh, discrete energy level, meaning that the transition is happening. If the transition is happening, if not, another case, but if the transition is happening, it will have the discrete energy level.
Exactly. If the electron stays in one energy level, it's stable there with its discrete energy. But when it makes a transition, say dropping from a higher energy level to a lower one, it emits a photon, with energy exactly matching that difference. This is why we see sharp spectral lines. The transitions are like the electron hopping between these fixed rungs on an energy ladder, always involving discrete energy gaps.
Okay. So if that energy level is not discrete, then it would have fall into the nucleus.
Not quite. Even if energy were continuous, the electron wouldn't just fall into the nucleus. The reason it doesn't is more subtle, due to quantum mechanics and the uncertainty principle. Classically, you'd think it would spiral in, but quantum theory sets stable states where the electron's wave-like nature prevents it from collapsing. Without discrete levels, you just have a continuum of energies, but the electron would still form a stable cloud around the nucleus rather than crashing into it.
Does that cloud also is a intuition that it is quantized, or cloud is just a probability where that with that boundary condition in that specified area the wave function evolves?
That cloud is exactly the probabilistic interpretation of the wave function. It's not quantized in the sense that the cloud itself is stacked. Instead, the cloud, the probability distribution, forms around allowed energy states. Those states are quantized. So the cloud shape changes from one discrete energy state to another, but within one state it's a smooth distribution. In other words, the allowed energies are quantized, and the cloud is how we visualize where the electron is likely to be in that quantized state.
Okay, what we have discussed till now.
We've explored quantization in quantum mechanics, focusing on how discrete energy levels emerge when particles are confined, like an electron in a hydrogen atom's Coulomb potential. The wave function must satisfy boundary conditions, leading to these allowed quantized energy states. When electrons transition between these states, we see discrete energy changes. Without quantization, we'd have continuous energies, but quantum principles prevent electrons from just falling into the nucleus. The cloud is the probability distribution, shaped by those quantized states.
So one question that boundary condition, how we can think and frame for the hydrogen atom.
In the hydrogen atom, we imagine the electron's wave function extending out into space. The boundary condition is that the wave function must vanish as you go infinitely far from the nucleus. Basically, the electron's probability of being infinitely away is zero. Near the nucleus, the wave function must remain finite and smooth. These conditions, no infinite divergence near the nucleus and vanishing at infinity, pick out the discrete, stable energy states we observe.
Is there any scale where up to that scale that that wave function will evolve beyond going infinity?
Yes, on the atomic scale, the wave function has its largest probability density near the nucleus, typically within a few angstroms 10 to the 10th meters. While the wave function mathematically extends infinitely, its practical significance diminishes rapidly. Beyond a few nanometers, the probability is negligible. So, while it technically extends forever, beyond atomic dimensions, it's effectively zero.
What about spin rule in quantization? Is there any relevance?
Absolutely. Spin is another intrinsic quantum property that is quantized. Particles have discrete spin values, like electrons having spin 1/2, meaning they can be in spin up or spin down states. This spin quantization is independent of spatial quantization, but interacts with it. For example, in atoms, spin orbit coupling, where the electron spin interacts with its orbital motion, creates fine structure, further splitting energy levels. So, spin quantization adds another layer to how we understand quantum systems.
Orbital motions are the dynamics that we observe for a two-body system in hydrogen atom also when the its own spin for the electron and proton interact with that dynamics. There we observe that thing.
Exactly. In a hydrogen atom, you have the electron's orbital motion around the proton, like a two-body system. Now the electron also has spin, and that spin interacts with the orbital motion. This spin-orbit interaction slightly shifts the energy levels. This is what we call fine structure. So in addition to the orbital dynamics, the electron spin couples to the orbit, causing tiny energy shifts we can measure.
How this energy shift happening because they are interacting with each other or there are energy transfer happening.
The energy shift comes from a relativistic effect. As the electron orbits, from its perspective, the proton is also moving, creating a magnetic field. The electron's spin acts like a tiny magnet. When the spin and this magnetic field interact, the energy shifts slightly depending on whether the spin aligns or opposes it. No energy is transferred between particles, rather, it's a shift in the allowed energy levels due to this coupling. It's a subtle correction, but measurable, hence why we see fine structure in atomic spectra.
One of the best example of quantization we can relate with the today's modern physics.
A perfect modern example is the operation of transistors in all our electronics. Transistors rely on semiconductors where electron energy levels are quantized into bands. The distinction between the valence band and the conduction band is a direct outcome of quantization. By controlling electron flow between these quantized states, we switch signals on and off, forming the foundation of computing. Without quantization, none of our microchips, processors, or modern devices would work.
Another example from quantum computing.
Quantum computing itself hinges on quantization. A quantum bit or qubit relies on discrete quantum states. For example, the spin of an electron or polarization of a photon can represent a quantized 0 or 1. Quantum gates manipulate these discrete states, and quantum algorithms leverage superposition, a uniquely quantized phenomenon. In other words, quantum computation is only possible because of the quantized nature of quantum states.
One from plasma.
In plasma physics, quantization is key when we talk about phenomena like Landau quantization. When a plasma, such as electrons in a strong magnetic field, forms, the electron motion perpendicular to the field becomes quantized into discrete energy levels, called Landau levels. This quantization governs how charged particles move in plasma, influencing everything from magnetized astrophysical plasmas to fusion devices.
In QFT.
In quantum field theory, QFT, quantization is fundamental. Fields, like the electromagnetic field, are quantized into discrete excitations. These are particles like photons. QFT describes how particles emerge from underlying quantized fields. For instance, the energy of these fields is quantized, giving us particles and antiparticles. Without quantization, we wouldn't have a consistent picture of particle creation, annihilation, or interactions.
In GR.
In everyday digital audio,
No,
we
no,
actually
wait, wait.
rely.
In general relativity.
In general relativity, we don't have a fully quantized theory yet, but attempts to unify gravity with quantum mechanics, like quantum gravity or string theory, propose that even spacetime itself might be quantized at the Planck scale. While we don't have experimental proof yet, the idea is that spacetime might have a discrete structure at extremely small scales, meaning gravity itself would become quantized.
So in hydrogen atom, what scale of quantization we are discussing?
In the hydrogen atom, we're talking about energy levels on the atomic scale. These are on the order of electron volts, tiny units of energy. The distances involved are around an angstrom, which is 10 to the minus 10 meters. So we're dealing with extremely small, discrete energy steps and spatial scales, well within the realm of atomic physics, but huge compared to, say, the Planck scale of quantum gravity.
One appreciation for quantization can you give?
One major appreciation is that quantization gives us a stable, predictable universe. Without discrete energy levels, atoms wouldn't form stable configurations. Chemistry, solid state physics, even the stability of matter itself, none of these would exist. In
Okay.
short, quantization is what makes the building blocks of the universe stable and allows us to build all the structure we see around us.
Okay, thank you.